Hello, good morning.
Good morning.
Shall I already share my screen?
Morning. Yes. Yes. Nice to have you.
Yeah, thank you for the invitation. It's a nice occasion.
Thank you for coming.
Let's see, is this looking good from your end?
Yeah.
Okay, perfect. So
Excellent.
then I will be back in a few minutes.
Yes. Great. Thank you.
So I'm ready whenever you are.
All right. Welcome, Professor van der Sijpen. And let me briefly introduce. So now we have Lieven van der Sijpen talking about spin qubits and quantum dots. And so Lieven van der Sijpen is a professor at QTech in Delft. There he leads a group that focuses on single spin qubits and semiconductor quantum dots for obvious applications in quantum computing and quantum simulation. He received his PhD in electrical engineering from Stanford in 2001, where he used the spins of atomic nuclei, which Vincenzo Savona mentioned before, in a molecule as qubits and implemented various algorithms, most famously Shor's algorithm. He then moved to Delft, first as a postdoc and since 2006 as Antoni van Leeuwenhoek professor. He collaborates closely with Intel for the fabrication of scalable and high-quality quantum dot arrays. I remember I saw a picture at the Array seminar in January of a very beautiful dot array. So I'm curious what we're going to hear today. Get away.
Okay, well, thanks, Uwe and colleagues, for the initiative to organize this school and for the invitation to lecture. I always enjoy speaking about this field. It's a field that I've been working in, well, in quantum computing for 25 years almost, and spin qubits in quantum dots for almost 20 years. And it continues to be my main research focus and my main passion. So this is not a conference lecture, of course. It's a school, and so even more than at conferences, I do encourage everybody to jump in with questions along the way. We will also take a short break because an hour and a half is a pretty long stretch, and yeah, I have some material at the end that I can leave out or not, depending on how many questions there are along the way. So you know, feel free to jump in. And the purpose is not for me to show off. The purpose is for everybody to learn. All right. So let's see. You know, the focus on the lecture is as Uwe said, right? Spin qubits, electron spin qubits in quantum dots. And what is a quantum dot? Essentially, a quantum dot is simply a small space in a semiconductor where one or more electrons are actually holes, but I'll mostly use the term electrons. One or more electrons are confined in a small space, small being 100 nanometers or less typically. And this region in the semiconductor is sufficiently well isolated from the rest of the material or from the rest of the world, so that the number of electrons that resides on it, the number of free electrons, you know, not the ones that are bound to the atoms, but the ones in the semiconductor that are free to move, that this is a fixed number. It's discrete, you can count it. And furthermore, because of the tight confinement, just like when an electron is confined to the volume around an atomic nucleus, you have these atomic orbitals. Also here, the space is small enough, the confinement is tight enough that the orbital energy becomes quantized. And at low temperature, these experiments that I will talk about are done typically in dilution refrigerators, you know, at 1020 millikelvin. At low temperature, you can then easily resolve this quantized energy level spacing, quantized motional energy. And so in a lot of ways, such structures resemble real atoms. And often people call them artificial atoms. The difference is they can be engineered, you know, we can control many of the properties in situ. We can turn lead into gold, changing the properties. And in fact, if we put more of these quantum dots together and allow tunnel coupling between them, you get artificial molecules. And we're even making small artificial materials by, you know, or small, well, I don't know. The distinction between a molecule and a material is a bit gradual, let's say, but at least we're looking at lattice physics as well. Let me give you some impression of the energy scales involved. The charging energy is a energy cost that you pay when you add charges to this small island with its capacitance to the rest of the world, C. And for a disk that's 1 nanometer in radius, the charging energy is actually larger, much larger than the thermal energy at room temperature. It's 300 milli-electron volt. Remember, the thermal energy at room temperature, it's at the bottom here, is 26 milli-electron volt. For a bit larger islands, let's say 100 nanometer, then the charging energy is 3 milli-electron volt. But still, that's a lot larger than the thermal energy in a DIL fridge, and even larger than the thermal energy at 4 Kelvin. The confinement energy level spacing, yeah, you see the numbers here. For a very tight confinement, it's even larger than the charging energy, 10 electron volt. And then for the typical quantum dot sizes, let's say 1 or a few milli-electron volt. Which means that these energy scales are well above the thermal energy in dilution refrigerators. And at the end of the talk, if I have time, I will show that some of this physics can also be seen at 1 Kelvin. But most of the measurements will be taken in DIL fridges because they're available, they're expensive, but they're available, they usually work, not always, and they're continuous operation and so forth. Now, there are, if you type quantum dot on Google, the first type of quantum dots that may come up are either small semiconductor pieces, just a few nanometers in diameter, crystals, little balls, or quantum dots that are formed by strain at the surface or at the interface of two different semiconductor layers. And actually, both at ETH and EPFL, there are top experts in such systems. These are typically optically active and probed with optical spectroscopy. And I just want to mention them so that there's no confusion. The type of quantum dots that I will focus on in this lecture, because these are the ones mostly used for spin qubits, they are defined electrostatically in a two-dimensional electron gas or in a quantum well. When our community started working on this topic of spin qubits 20 years ago, the workhorse was gallium arsenide, aluminum gallium arsenide heterostructures. So there is a gallium arsenide substrate, and then a top layer, say 100 nanometers thick, with 30% aluminum or so. And the band gap between these two layers is different. And all the free electrons in this system provided by the dopants in the substrate, all the free electrons would then be confined at the interface of these two layers. That's the blue sheet. So it's a two-dimensional electron gas. And it's a system that's been very much studied also for quantum Hall physics, mesoscopic physics. It's been a very, very powerful, flexible system. And the flexibility comes in great part from the fact that with voltages applied to gate electrodes on the surface, and you see here a scanning electron microscope image of an actual gate pattern. If you apply a negative voltage to such a gate, then underneath you can push away the electrons, which carry a negative charge. And so all the regions indicated in orange here are depleted of electrons. There are no more electrons there. And you can imagine that with the right geometry and the right gate voltages, you can then form small spaces which are isolated from this reservoir of electrons with a tunnel barrier, a potential barrier. And they're separated by a potential barrier, and depending on how tall and wide it is, electrons can tunnel through and it becomes a tunnel barrier. And so that small space then is what we call a quantum dot. It's kind of pancake shaped in this case because the thickness of the quantum well or of this 2D electron gas is maybe 5 nanometers or so, and then the lateral dimension is tens of nanometers or 100 nanometers. And here you see a second quantum dot, and electrons can then actually flow. If you apply a bias from here to here, electrons can enter this quantum dot and then move on to the other one and exit from the other side, and you can actually get a current through. And our community has learned how to interpret that current to identify how many electrons are on the dots, what orbitals are occupied, even what spins are occupied, and so forth. But most of the measurements today in our broader community happen not by measuring current through the quantum dots themselves, but instead by measuring current through these external constrictions. In this case, they are just quantum point contacts, as we call them. And as it turns out, the conductance through this constriction depends not only on the gate voltages, that determines how wide the constriction is and thereby what the conductance is, but it also depends on how many electrons there are on this quantum dot. The electrons, as you add an electron to this quantum dot, the single charge of that electron will also appreciably change the width of this channel. It will change the conductance by 1% or so. It can be even more, and that's easy to measure. And I'll show you how these external charge detectors, as we call them, because they probe how many charges there are on the dots. These are used extensively. So that's gallium arsenide. That's how we started. But in the last 10 years, most of the work has shifted increasingly to silicon platform. Here you see a schematic of a design that's very popular nowadays, where you have some implanted contacts here and here, and then you have some gates. Well, you know, let's actually take for comparison a transistor. What is a transistor? Well, you have a contact, you have another contact, and then you have a gate electrode that covers the space between the contacts. If you apply a positive voltage to the gate electrode, you pull electrons towards, well, I should say there's also a thin dielectric on the surface, and then you pull the electrons towards the dielectric, and then, you know, the electrons can flow from one contact through that channel to the other contact. That's how a transistor works. It's a switch. So in the quantum dots, that gate electrode is replaced by a split gate, as we call it, so several segments. And then if you look at the potential landscape along that red dashed line, we can shape it, for instance, as in the bottom left image, where some voltages have a more positive bias. Some gates have a more positive voltage than others, and you can really shape the potential landscape. So here there is lots of electrons in the reservoir, then there is a potential barrier, and then there is a potential minimum where one or more electrons can be trapped, another barrier, and so forth. And so here you see an actual SEM image of, you know, showing a similar set of gates. And then on this other side, you know, so the qubits will sit here, and then this will be our charge meter to probe what's going on with the qubits. Same concept. And you see here the cross sections, right? The most popular geometries of the material stacks are either the basic transistor structure, how it was developed many years ago, a silicon substrate, silicon oxide dielectric, and then a gate metal, and then the electrons reside in the silicon right against the oxide. Or you can have buried silicon, but then separated from the gate oxide with silicon germanium, which again has a higher band gap, so electrons will be stuck in the silicon. And the advantage is here that the electrons are farther away from the dielectric and from the surface, and often dielectrics and surfaces are the source of charged impurities that kind of spoil the potential landscape, so it doesn't look so clean. And in this case, it's going to look cleaner than here. Yeah. So then, you know, schematically, these structures look as follows, right? You have the source and the drain contacts. The island, electrons can tunnel on and off, and that is kind of regulated by the gate voltage, which controls this electron flow. So these quantum dots, like you can see, they're defined electrostatically, they're measured electrically, there is no optics involved. Here is some actual data of that charge detector signal. So here you see 3 quantum dots in a row. In this case, the charge sensor is itself also a dot, a bit of a larger dot. And what's plotted in color scale is the derivative of the current through this quantum dot. And anytime that an electron gets added here or moves, there will be a jump in the current. And after taking the derivative, the jump becomes a spike, and that gives rise to these lines in the color plot. And so out here, the two, well, this is now just scanning 2 of these gate voltages, looking at the triple dot like a double dot system, and out here, both of them are empty. If we pull with the voltage P1, we will pull in an electron on the left dot, If we pull in with voltage P2, we pull in an electron on the right dot. If we pull with both, there is one electron on both dots, and so forth. And the angle that you see here, the slope in these lines, is because there is crosstalk. In this right plot, the crosstalk is compensated because we apply combinations of gate voltages. That's what we do routinely now. So the way that these quantum dots and the spins in them are then manipulated and read out is by making use of rapid voltage pulses applied to the gate electrodes and RF or microwave excitation applied either to the gate electrodes or to external structures that I'll mention in a moment. I see a question here. The design looks rather complicated. It doesn't seem to have a specific pattern when you compare different circuits. Okay, yeah. I would say that we started as a community with this type of design for reasons that I'll maybe skip over. A design like this, to me at least, it looks pretty straightforward in the sense that you can imagine that this voltage mostly controls the potential of the island. This voltage controls mostly that barrier. There is some crosstalk and we compensate for it, but at least here you can see a little bit. Admittedly, some of these designs, especially this one here, when I first saw it, I had to think a long time which gate fulfills what function. I will admit that. I think I'll say that as a community, we have moved towards actually more transparent designs, kind of this fashion, where the functions are, the functions of the gates are easy to read, and that has helped us to do it more quickly. This being said, we have also gotten better at compensating for crosstalk and don't worry about crosstalk as much anymore. Yeah. And then other aspects, how do we look if a design is good or bad? Obviously, the dimensions play a role, and based on experience, we know what's going to work and what doesn't work so well. Yeah. Let's see. I get the note. Okay. Yeah. Why is the charge measuring quantum dot placed not with an offset and not directly on the opposite side? Yeah, if we look, for instance, at this image here, it's placed such that you can also detect charges that move between quantum dots. You can imagine that if the distance, let's look at this design here, right? It's easy to see. If I had placed the sensor in the middle, then we would have the same change in the current when an electron is added to this dot versus that dot. And then it becomes hard to distinguish them. And that's why we place them on purpose asymmetrically, so that the signal from all of the dots is different, and we can tell which signal corresponds to what change in the dot in the electron configuration. And also we place it such that we are sensitive to charges moving between dots. If we were to place this one exactly in the middle between these two dots, we wouldn't be sensitive to a charge moving from here to here. And so these considerations decide where we place the sensors. Yeah. So excellent questions. Thanks. So what I'm going to do is essentially, in much of the remainder of the lecture, I'm going to take you through the DiVincenzo criteria, which I presume or hope you're familiar with. In order to have a quantum processor, you need to be able to initialize your qubits to read them out. You need universal control. They need to be coherent. And of course, you need to have a scalable register, which is not explicitly part of here. I see another question. The fact that not every dot has direct access to the reservoir, is that a problem? Well, it's a complication, but we have learned to work with it. And later on, and so basically what we do, to reach the middle dot, we will have electrons pass through the ones on the outside. And we have learned, for instance, how to tune up 8 dots in a row without much difficulty, just by forming them one after the other and filling them one after the other. And so, yeah, I think some years ago, people tried to find ways to get reservoirs close to every dot, but is of course an approach with limitations, and I've pushed to not having to do that. And as a that's basically it's not a big deal anymore. We can work without that access. Yeah. Okay. So yeah, I will then take you through these steps, right? How do we initialize? There are two popular methods. The first one is no longer so popular because it's slow, but it's easy to imagine. If your thermal energy is several times smaller than the qubit splitting, you can just wait for the system to thermalize. I'll show you in a moment that the thermalization time, the T1, the relaxation time, can actually be really long, which is good for many things, but not for rapid initialization. And therefore, what we do more often, for instance, is to start with a dot that's empty by pushing the level. Well, these are the spin up and the spin down split states, electrochemical potentials, as we call them. So that's the energy. The line here. The line here. Actually, let me perhaps. Oops, sorry. Move to the laser pointer, that's sometimes a bit more visible. So this line here indicates the energy needed to add the first electron of the dot if it's a spin-up electron, and that is the same energy when it's a spin-down electron. In this case, both are above the Fermi level in the reservoir, so the dot will be emptied. If we then pull the levels down with a gate voltage pulse to this configuration, the dot will be filled, but necessarily only the lowest spin state can be filled. So that's a way to initialize, and that can be done on a timescale controlled by this tunnel rate here, and that tunnel rate can be made very fast with the gate voltages. So that's how we often initialize. There are other methods, but yeah, I can't go through every method, of course, in this lecture. Sorry. Yeah. So then for the spin readout, let me take you an intermediate step and show charge detector signals, but now in real time. Here you see a time axis, and it's plotting the current through this constriction under a condition where an electron can hop on and off the dot. The alignment is basically like here. In the middle, it's equally energetically favorable for an electron to be in the reservoir or on the dot. Here, it's most likely going to be in the reservoir, here most likely in the dot, but still once in a while an electron will tunnel out. Here once in a while an electron will tunnel in, and here it's roughly 50-50. And you can see it really in real time. You can follow as the electrons move in and out. Now let's take one step further. Now we apply a gate voltage pulse, and I'm now leaving out the spin details. Gate voltage pulse taking us between these two positions, going through this cycle. Starting from empty, we rapidly go here, an electron will tunnel in, we rapidly go there, an electron will tunnel out. If we now look at our charge detector signal, we will see a combination of two things. First, the current through the charge detector also responds to that different voltage on the gate. So it responds to the pulse. That's this step here. And then soon afterwards, at a random time, it's a Poisson process, the electron tunnels out, and the step, you see a response to that tunnel event. And then here again, the pulse is removed. And then in this case, very shortly after, the electron tunnels in or tunnels out. So you get these two contributions to the charge detector signal. And now we're going to combine them to read out spin states. In this case, we will read out the spin state of one electron in a single shot mode. And so to test this protocol, we do the following. The dot starts empty, and then we pull the levels down, but such that both spin states are accessible. So randomly, the dot will be occupied with either a spin down or a spin up electron. And next, we'll attempt to read that spin state. And we do that by going again to this intermediate configuration, where if the lower spin state is occupied, the dot will remain occupied as well. The dot will remain filled. This electron does not have enough energy to escape to the empty states in the reservoir. Whereas if it's the upper spin state, the higher energy spin state that's occupied, then that electron will tunnel out to these available states in the reservoir. And after it tunnels out, it leaves behind an empty quantum dot, which will be refilled with an electron of the lowest spin state, the spin up state. But for a brief moment in time, here the dot will have been empty, and so there will be this step expected in the charge detector signal, whereas we expect a flat response if the electron is stuck on the dot, right? And then afterwards we empty. And so that's an experiment that we tried for the first time in 2004. This is work from us in Delft. Oh, I see a question here. Is it easy to tune this intermediate energy level between the two spin states to read out? Essentially, yes, nowadays. Yeah. So let's see, I'm gonna have to switch back to the mouse because I need to move the Q&A inside and outside my view. Okay, sorry.
If you prefer, Lieven, I can also read the questions to you when they pop up.
Well, okay, let me ask, can you easily see the mouse?
Yes, we can see them.
Okay, then we'll just do it like that.
Okay.
Yeah. So yeah, I mean, it's pretty straightforward. We have systematic methods to identify that condition. Yeah, fortunately. Yeah, so here you then see the response, right? The combination of gate voltage response and tunneling, and then here is the readout segment. Here the response is flat, so we conclude the spin state was up. Here we see a little blip, so we conclude the spin state was down. And that works most of the time, not perfectly, but most of the time, and over time that measurement fidelity has become pretty high. In some cases, yeah, not particularly this measurement scheme, but some spin readout demonstrations have certainly gone beyond 2 nines. Some have also reported 3 nines. It's very hard to be certain when you're claiming such high numbers. You need to consider all the errors that can happen, but these spin readout can be pretty reliable these days. So how did we test back in 2004 that our readout was working? We would increment the time between the moment the electron was injected and the time we started the measurement. And naturally, the longer you wait, the more time you give the electron to relax to the ground state. And the lower the spin down fraction should be. And that's what we saw. We saw this exponential decay, and that gave us confidence that our spin readout was returning something sensible. Because at the time we weren't able to rotate the spin yet. So here you already saw the long relaxation time, in this case a millisecond. Compared to orbital relaxation timescales, this is much longer. Orbital relaxes in tens of nanoseconds. Actually now or afterwards, there have been measurements seeing T1s well over a second. In some cases, in exceptional cases, even about 10 seconds T1s. So that's extremely long relaxation timescales. Of course, any timescale needs to be compared to the other relevant timescales, which we will come to in a moment, the manipulation, but these are all much faster than the relaxation. The dominant relaxation mechanism is the following. The energy is transferred to the phonon bath, the lattice vibrations, and the phonons couple to the spin through the spin orbit coupling. It's basically the electric field fluctuations from the phonons that interact with the spin through the spin orbit coupling. And this indirect coupling of electric fields to spin via spin orbit coupling will also come back in the control in a moment. And we know it's phonons and the spin orbit mechanism from the very steep dependence of the relaxation time on the magnetic field. Look at this, a 5th power dependence. So going to low field very rapidly, the T1 just goes through the roof. So here then are the first data. This is also from our group in 2006. First data showing coherent control of a single electron spin on such a quantum dot. And the coherent control was achieved using magnetic resonance. That is to say, you have an oscillating magnetic field on resonance with the spin transition energy. And you know, the longer you apply that resonant magnetic field, the more times you rotate the spin around the Bloch sphere. And then I'll skip through the details of this particular axis here, but it is effectively a measure of the spin probability. And these curves are offset from each other. And you see that that spin probability oscillates roughly sinusoidally as a function of the time that we apply the burst time. And so that's indicating that we're taking our spin here through Rabi oscillations. The oscillating magnetic field was produced by sending an oscillating current through this very short piece of metal that you can see it sitting on top of the quantum dot gates. And that oscillating current, of course, produces an oscillating magnetic field at the dot location through Ampere's law. And let me actually just remind you, right? If you have a current through a wire, you get an oscillating field, you get a magnetic field around it. If the current oscillates, the magnetic field oscillates. Now, this oscillating magnetic field, if we look from the top in the Bloch sphere, it will go back and forth like this. And we can decompose it into one component that rotates clockwise and the other that rotates anti-clockwise. And if one of them rotates in the same direction and at the same rate as the spin precesses around the static magnetic field, then it's able to drive that spin resonantly. Actually, let me attempt, it's a bit hard now online, but I always like to do this little spin dance, and I will perform my spin dance for you to explain intuitively this, you know, the motion of the spin, right? So let's see here. So we have a vertical magnetic field, a static magnetic field, and our spin, okay, that's the vertical magnetic field, our spin will precess around the magnetic field, the static magnetic field. That's what the spin does. You know, in the Hamiltonian picture, it's a sigma z evolution. Now imagine that you now apply a transverse magnetic field. So perpendicular to the external field, transverse magnetic field, and that rotates around at the same rate as the spin. Then for the spin, this rotating field actually looks static. If you imagine that you're moving yourself on a merry-go-round, you're putting yourself on a merry-go-round, and you're rotating around on this merry-go-round, the rotating field is no longer rotating, it looks static, and to the spin it looks static. So what the spin will do is to precess around that field that looks static to the spin. So I noticed that with the angle of my camera, this is not working as well as I hoped, but in this way, you can see that that the spin, you know, and this is the picture here, in the rotating frame, it rotates around this axis, around this field, which in the rotating frame looks static, but in reality is rotating. And so that will be then the trajectory of the rotation of the spin around that axis. If you put yourself in the laboratory frame, then that rotation actually becomes this spiral trajectory on the surface of the Bloch sphere. And then depending on how long you apply it, you know, you can take a spin from spin up to spin down, or you can take it from spin up to a superposition of up and down and so forth. So now notice that these were the first rotations. And at the time we were, of course, very happy to see them, but you will, if you know, you will have remarked or should have remarked that the quality of the rotations is not so fantastic, and I'm going to come back to that. Before doing that, though, I wanted to comment on two other methods that we have developed to control the spin. The first one also comes from our lab, and it uses the same spin-orbit coupling that allowed the phonons to talk to the spin. That same spin-orbit coupling is now used to allow a applied AC electric field to talk to the spin. So we apply to one of our gate voltages. In addition to the DC voltage used to bias the dots, we apply an AC excitation to it, and that will wiggle the electrons around inside the dot confining potential. And because of spin-orbit coupling, if you move an electron through a semiconductor, it experiences an effective magnetic field. And that effective magnetic field is oriented in one direction if you move in one direction. Well, moving in this direction, you rotate one way, and moving in the other direction, you rotate the other way. Or in other words, the magnetic field orientation that is the effective magnetic field that the spin experiences oscillates as its direction of motion is oscillating. And now the spin experiences there's an effective magnetic field that's oscillating. If you apply that oscillation at the right frequency, you get a magnetic resonance condition effectively. And we can again get Rabi oscillations. It's quite remarkable that the Rabi oscillations were about as fast, almost as fast, as with this direct magnetic driving. This method is still used today as well. And there is a third method which has probably been used the most if you look at the literature. Although I don't know yet if that's the one that's going to survive. This one came out of the group of Seigo Tarucha, and here they replaced this spin-orbit field by an externally engineered gradient magnetic field. So there is a small piece of magnetic material like cobalt placed next to your quantum dot. This will produce an inhomogeneous magnetic field at the dot location. And if you then use the electric field to wiggle your electron back and forth, then the electron will literally experience a oscillating magnetic field. And if that has the right orientation, orthogonal to the static field, and again, if that oscillation happens at the right frequency, you get again magnetic resonance. This technique has especially become popular in silicon because in silicon, the intrinsic spin-orbit coupling is very weak. And I will in a moment, actually now. So why would we move to silicon? And why were the rotations in these early experiments not so fantastic? Why did they damp rather fast? It's because of the hyperfine interaction with the nuclear spins. So in gallium arsenide, all the gallium and arsenic atoms that exist in the universe carry a nuclear spin. There are no spin zero isotopes of gallium or arsenic. And these nuclear spins interact with the electron spin. Or let me put it this way, if the electron spin will interact with the nuclear spins that the electron wave function overlaps with. It has a certain spatial extent, and wherever the electron resides, there will be a hyperfine interaction with the nuclear spins in the lattice, from the lattice. Does that make sense? And now the nuclear spins, even though we operate at a few Tesla and at 1020 millikelvin, the nuclear spins will barely be polarized because the magnetic moment is so weak they barely align with the field. So there you can imagine them pointing in random directions, and every time a little bit different directions. And as a result, the electron spin experiences from the nuclei a random influence. So we call it an effective magnetic field, an Overhauser field, which is random. And the result of this randomness is that within 10 nanoseconds, if you just let the electron spin evolve by itself, within 10 nanoseconds, it has evolved on the Bloch sphere into a direction that you have no idea anymore. So you lose track of the spin state. Okay, that's what we call decoherence, right? That's decoherence. What we knew from the start is that if it were possible to make similar devices in silicon, things would be better. Because in silicon, only 5% of the atoms have a nuclear spin, the silicon-29 atoms. And indeed, this is work from our group, and actually Pasquale Scarlino, who will speak this afternoon, together with Erika Kawakami, did these experiments. We found that this T2 star timescale went up by a factor of 100, moving to silicon. And parallel work from Andrew Zurek at UNSW, led by then postdoc Menno Veldhorst, who is now also a group leader at QTech, saw another factor of 100 improvement after isotopically enriching the substrate and only having mostly silicon-28 atoms there. So a factor of 10,000 improvement in coherence, moving from gallium arsenide to enriched silicon-28. I can tell you that really changed my own view on the promise of our fields. You know, when we were doing gallium arsenide only, I was seeing the limitations. You know, of course, our entire field is challenging, but it looks not so good. But then seeing the results from silicon, you know, that gave a major boost to my optimism that we can really get somewhere. And this 100 nanosecond or microsecond timescale is not the end of it. Using spin echo and dynamical decoupling techniques, it can be extended further to tens of milliseconds. The half a second here, that's not from a quantum dot, it's from an impurity, but the physics is similar. But so yeah, up to tens of milliseconds in quantum dots at the moment. And actually, I will explain a little bit more in a little bit more detail the you know, how you extend the coherence by these echo techniques. I'll come back to that. But so if you now compare these old oscillations with the 2014 oscillations from Menno, you know, you can understand why I got more motivated or confident, right? It's just beautiful. Almost no decay visible after some 10 oscillations. The fidelity of the operations has also been quantified. Here's work, for instance, from the Tarucha group, seeing well over 3 nines of fidelity on the single qubit gates in silicon. And so that's looking promising. So then, how do we extend the T2 star from the, how do we extend the coherence from the T2 star timescale to these even longer timescales? So here's the way that the T2 star is measured. You rotate your spin into the transverse plane. You let it sit by itself. After a variable wait time, you attempt to rotate it back. But it could be that the spin has drifted into a random direction, and then this attempt to rotate it back will not fully work. And that's why you see the decay here in the oscillation, right? And that time scale is, yeah, in this case, 120 microseconds, which is already quite long. But now let's stick a pi pulse in between. Then the evolution, the random evolution that happens during the first interval can be reversed during the second interval. And I have a little animation to illustrate this. So here's the first 90-degree rotation, taking the spin at the transverse plane. And then because of the interaction with the environment, the spin will pick up a random phase that happens on the 100 microsecond time scale. Now, at some point, we apply, then we apply a 180-degree rotation. That's what's going to happen here, right? All right. The 180-degree rotation. And the spins that were running behind are now running ahead, and the spins that were running ahead are now running behind. And if you allow them to evolve for the same amount of time after that echo pulse, then they all come back together. That's called a spin echo effect. So look here, look at the ones running in front and behind, and eventually they all come back together. So that's a spin echo. And here there is a single echo, but you can imagine that this echo is only effective when the random influence from the environment during the first and second waiting interval is the same. In reality, it's never perfectly the same. You know, the environment also evolves. And then to extend the coherence further, what you can do is to stick more of these pi pulses in your waiting interval, so that the time between them is shorter and the environment will have evolved less, and the refocusing from the echo effect is better. And in this way, you know, you go from a 1.2 milliseconds single pulse experiment, that's called the Hahn echo experiment. You can go in this case to 28 milliseconds. Here you see data where the number of pulses is increased, and yeah, this is now on a semi-log scale, and just the coherence gets extended as you add more and more of these decoupling pulses. So I think this is a good moment to take a short break. Let's just take a few minutes, enough to take a breath, and we'll continue in a few minutes. All right.
Yeah, thank you. Are we allowed to ask you more questions, or
Yeah, of course, yes.
Gonna get a glass of water and stretch your legs?
Well, I am gonna, well, both.
Okay.
Yeah. So well, let's first take some questions if there are questions. Yeah.
I had one. Actually. You mentioned the dephasing due to the coupling of the charge degree of freedom via this static magnetic field with a piece of cobalt. And I was wondering what exactly controls the level separation, this confinement. When there's a bunch of probably effects because it's a very densely packed system. So I assume it's like a collection of different effects, but all of these, you would probably have to think about when thinking about the dephasing, right?
Well, let's see. So I didn't emphasize this very much, that the gradient, well, what I emphasized is that the gradient from the micromagnet can be used to drive spin rotations. And in particular, it's when we call it the transverse component of the gradient is present. The transverse meaning the electric or the magnetic field component that's orthogonal to the large externally applied field. If that is inhomogeneous over the dot trajectory, then you get an oscillation in the field it experiences. In addition, also the longitudinal component of the micromagnet gradient can be present, and so if you then so that adds to the external field. And now what I didn't mention, but I'll mention it here, if you have charge noise that wiggles your electron position in an uncontrolled way, then depending on the electron position, the spin splitting will be slightly different, and that leads to phase randomization and to dephasing. And so the presence of this longitudinal gradient makes the spin sensitive, vulnerable to dephasing from charge noise. Now, what we have done in our experiments, especially in the later experiments, is to design our micromagnets such that the longitudinal gradient is small and the transverse gradient is large. We don't want the longitudinal gradient to be zero, because what it also does is to shift the resonance frequencies of adjacent quantum or of spins in adjacent quantum dots. It separates these resonance frequencies from each other. But we make it not too large so that we're not too vulnerable to decoherence. And extending this scheme into larger systems, larger arrays, will need more thought how to engineer that gradient properly to make everything match. And of course, there are limitations from Maxwell's laws to what's feasible there. Yeah.
I see. Okay. So I think
did that answer the question?
Yeah, I think it did.
You don't sound really convinced.
I have to think about it a little bit, because so what I thought was that there must be many other things that couple to the sigma z degree of freedom that didn't cause the phasing noise. And obviously the sigma x noise doesn't seem to be a big issue here, since the T1 is so long already.
That's right. Yeah. So the sigma x only can, well, so the spin flips, they only occur when energy can be dissipated, and that is then dissipated in the phonon bath.
Yeah.
And that's just rather ineffective.
Yes. That's great.
Now, the transverse gradient that we engineer, the larger we make it, the shorter the T1, the more efficiently the phonons will couple. But the fact is we have a lot of margin on T1, so that's okay.
Yeah.
Maybe that was the question that you were asking.
My question was what else couples to the sigma z?
What else? The dominant mechanisms are charge noise coupling in via the longitudinal gradient, one, and two, hyperfine noise, although or nuclear spin noise, although in the isotopically enriched samples that becomes very, very small at some point. Yeah. So yeah, but if you have no engineered gradient, then the hyperfine noise can be also limiting. And then there are other effects, just from intrinsic spin orbit coupling, the spin splitting can be slightly dependent on the electron position. And then you also become sensitive to charge noise. These elements or these aspects come into play once you're talking about really long or really small effects, hence really long decay times. But eventually they also come in.
And heating from all the DC voltages, or
the DC voltages don't cause heating, but the pulses in the microwave drives do cause heating. They will eventually accelerate the T1 from, a T1 process is essentially spontaneous emission of phonons. And then now it becomes also not only spontaneous, but also stimulated emission. And the T1 times do drop with raising temperatures. T1 or thermal effects or heating can also activate charge noise or not. It depends on whether the charge noise happens by tunneling, which is temperature independent, or by thermal activation. But yes, in general, we do see that as we warm the samples up, that the devices get more noisy through these mechanisms.
Expected, I guess. Yeah.
Yeah. Well, except for tunneling, that's not temperature dependent. And also hyperfine noise is not temperature dependent, but charge noise, in practice, it can be thermally activated. Yeah.
Okay, cool. Thank you.
More questions?
Maybe it's glass of water time.
All right. So let's take 3 minutes or so. Not very long. Okay, in a moment. See you in a moment. All right. I see another question. Okay, yeah, what are the advantages or disadvantages? I will actually, that's a great question, and maybe I should have started giving some perspective at the start. But I will come back to that in a little bit. Well, actually, let me already emphasize one thing. So, seem to have a similar strong interaction with the environment like superconducting qubits. Well, not really, right? Superconducting qubits, at least, I think especially the ones that are fabricated, on a substrate, not the 3D cavities. T1s are hard to go beyond 100 microseconds. The T1s of spin qubits are easily a second, and so that's much longer. And also the T2s, the T2 star is comparable to the decay time scales of superconducting qubits, perhaps, but it can be extended much more using dynamical decoupling than is the case for superconducting qubits. So I think it's fair to say that the coherence of the spin qubits is really better than of superconducting qubits, at least today, that's really an advantage. There are other advantages which are going to become clear as we carry on. And then I see another question. You have to perform the spin echo technique to keep T2 as long as possible. That's true. And it means that you need to apply lots of pulses. Based on experience, from the time that I worked on NMR quantum computing for my PhD, that's something that in the end you just learn to deal with. It becomes part of your thinking to just add those decoupling pulses. And the thing about it, it's very transparent how to do it. And it's very easy, therefore, to compile into your circuits. So that's not typically seen as an actual obstacle. Okay, so where are we now, right? So we've spoken about initialization, spin readout, and single qubit operations. What is going to come now is a different way for reading out, because it's also used a lot. And then 2 qubit gates, and the physics of these two are very related, of that readout and of the 2 qubit gate. And then I will end with some scaling perspectives, talking more about the advantages of the platform, the strengths of the platform. Okay, so we've seen one way to read out spins. Here is a second method. It's also very popular. It uses the fact that quantum mechanics does not allow 2 fermions to occupy the exact same state. And so specifically, what that means is the following. On the same orbital, you can have 2 electrons with opposite spin, actually a singlet, so it's antisymmetric. But if the 2 spins are identical, they cannot occupy the same orbital on the same dot. So this state is allowed, one in a different orbital and then one in a lower orbital, but they cannot be both on the same orbital. And that fact can be used for readout as follows. You have one electron on one dot, another on the other dot. And what we will do now is compare the 2 spins. If the spins are opposite, they can come together on the same dot. If they're the same, they cannot come together on the same dot because the higher level or the higher orbital here is not energetically accessible. So this is a different, as we call it, spin to charge conversion mechanism, a different mechanism whereby the electron position or occupation of the dots is made to depend on the spin state. And then just like before, if we simultaneously, while this is happening, look at our charge detector signal, we can conclude that the spin was either these 2 spins were opposite or they were the same. Strictly speaking, singlet and triplet. If you wanted to read out a single spin, then what this qubit would act as a reference qubit to read out this one, but also oftentimes we want to read them out collectively. And then this is also a good way to go about it. Now, that same Pauli exclusion principle also underlies the 2 qubit interaction. Here you see a cartoon or an energy level diagram, where on the left, there is one electron on each dot. That's the most energetically favorable condition. And then here, the most favorable condition is 2 electrons on the same dot. But again, that's only possible if it's a singlet that's formed. If a triplet is formed, then the electrons have to stay on their own dot and you're on these levels. The result of that is that there is an energy difference between the singlet and the T0. That's this energy difference. If we zoom in, it's over here. And if you have an energy difference between singlet and triplet, it means that there is an exchange interaction acting on your spins. In fact, anytime that you make 2 electron wave functions overlap a little bit, there will be an exchange interaction acting on the spins. The Heisenberg exchange interaction, it's written compactly here. It's XX or sigma x plus sigma y plus sigma z. And what we then do in the lab is to briefly allow the electrons to overlap and interact and have their spins interact, separate them again, and in this way control the time evolution under the exchange. That was done for the first time in 2005 at Harvard, actually before the single spin control was seen or achieved. And here you see these oscillations that are indicative of oscillations between the spin up, the up-down state, going to the down-up state, and back to the up-down state, and so forth. That's what the exchange does. It literally exchanges the spin states. The parallel states, if you exchange them, they stay the same. They're unaffected. Of course, if you start from up-down, you rotate to down-up, but you stop halfway, well, my fingers won't tell you, but that's actually an entangled state that you reach halfway. It's a superposition of up-down and down-up. So this is an entangling gate. It's a 2-qubit gate, and combined with single qubit rotations, it gives you a universal gate set. That was not done yet back then, but at least the essential mechanism was shown back then. Note that these exchange oscillations can be very fast. The time scale here is nanoseconds, and some of the periods here are sub-nanoseconds. Note also that they decay quickly. It's because of combination of charge noise, of nuclear spin noise. This was gallium arsenide back then, but also charge noise. And the reason that charge noise was also affecting the oscillation is that early experiment, that first experiment, was done away from the so-called sweet spot or symmetry point. What was done basically is to go from electrons that are both in their own dot, and then the overlap between the electrons was enhanced by tilting a bit the potential of one dot versus the other, so that this dot, the electron wave function here, would leak a bit into the right side, and then they would start to, there would be an exchange interaction acting on the spins. But the overlap here is to first order sensitive to charge noise because it modulates that detuning. Whereas in contrast, if what you do is to increase the overlap between these wave functions, not by tilting, but by lowering the tunnel barrier, then you're in the symmetric condition, and to first order, the exchange strength is not sensitive to charge noise. And so here is then more recent data. This is from Copenhagen, showing quite beautiful exchange oscillations at this symmetry point. Now, let's see. Let me, for the sake of time, skip through this. Let me just state that in silicon, there are some additional complications that have to do with an additional degree of freedom that exists, the valley. And if you know what it is, then good. And otherwise, I'm just going to skip over it for the sake of time. All right. So this exchange interaction is the mechanism that underlies all of the 2-qubit interactions in these experiments. Although in many experiments, the flip-flop terms in the exchange have been suppressed because of the difference in the qubit splittings. So we spoke earlier about the micromagnet leading to a different splitting of one qubit versus the other. That's helpful, so you can individually address them by picking out specific frequencies. And this energy difference will suppress the flip-flop or the effect of the flip-flop terms. And so effectively, the interaction that remains is only the ZZ interaction, that's the Ising interaction. And the effect of the Ising interaction is to shift the anti-parallel states relative to the parallel states. And you can use that interaction in two ways. You can use that shift in order to selectively drive this transition or that transition. These are not identical anymore. If the coupling is off, this transition is identical to that one. The flip of the first qubit does not depend, or the qubit energy of the first qubit does not depend on the state of the second qubit. But as we turn on the tunnel coupling, that's no longer true. Depending on the state of the other qubit, the first qubit splitting will be slightly smaller or larger. And that means we can selectively drive one spin conditional on the state of the other. Of course, a conditional rotation, that's a 2-qubit gate. It's very close to the C0. It's not exactly the C0, it's a C-rod, conditional rotation, but it's very close to the C0, at least for the right timing. And another gate that we can implement using this Ising interaction is a C-phase gate. In this case, you just start from the uncoupled situation and you move adiabatically to the situation with coupling, where again, the splitting of one qubit depends on the state of the other qubit. And that means that there is a ZZ, well, there is a conditional phase evolution. One qubit will precess more rapidly or more slowly, depending on the state of the other. So that gives you not a controlled knot, but a controlled Z, or controlled phase evolution. That's also a universal gate. And so all of these schemes are used in experiments, are reported in the literature. I think eventually from theoretical analysis, my understanding is that the C-phase gate has the best potential for the highest fidelities, but all of them can actually work quite well. And to give you some numbers of the state of the art, a few years ago, 2 years ago, the Jurek group published a 98% fidelity for the 2-qubit C-rod gate. And we published a 92% fidelity for the C-phase gate. And we're now finishing a paper where we report a 99.5% C-phase fidelity. So well above 99%, which is often seen as sort of a magical threshold. It's not really strict, but at least it's often seen as a threshold for reaching good enough fidelities that you can do error correction and be fault tolerant. Which means that both the single and the 2-qubit gate rotations, or 2-qubit gates, sorry, are now well above this 99% threshold, and that's a good place to be in, and there is room for further improvement. So what we've covered now is how to initialize, basically usually by selective tunneling, spin selective tunneling, how to read out by making the spin move to another dot or to a reservoir or not, depending on the spin state, and then recording the charge occupation using the charge sensor. We've seen how to rotate individual spins by applying oscillating magnetic fields or oscillating electric fields that then effectively still produce an oscillating magnetic field, so magnetic resonance. We've seen that the pulsed control of the exchange or of the overlap of two electron wave functions allows 2-qubit gates based on the exchange interaction, and the flip-flop terms sometimes can be suppressed, and then it becomes a Ising interaction. And we've seen that the T1s are really long, more than a second, and also the T2s actually are quite long for solid state qubits compared, for instance, to superconducting qubits. I do want to briefly mention that in addition to the approach where a single electron spin encodes a qubit, there has also been work encoding a qubit into the collective state of two spins, the singlet and one of the triplets. And also in the collective state of three spins, actually some beautiful work at ETH, for instance. Collective state of three spins. The advantage of these encoding schemes, for instance, the last one here, it doesn't require microwave drives. It can operate with purely gate voltage pulses, and that can be, from the fabrication technology point of view, can be advantageous. It also doesn't need, wires to pass oscillating currents. It doesn't need micromagnets. On the other hand, the encoding also introduces complications. You need more dots for the qubit. Okay, that's in the beginning slowing you down. Eventually, it won't make a big difference. But more importantly, I think the biggest downside of this encoding, is that in order to perform a single qubit operation, you need something like 5 or 10 evolutions under the exchange. And then to get the same fidelity, it means that the underlying exchange fidelity needs to be, 5 or 10 times better to get the same effective fidelity on your qubit. So the last word hasn't been said. There is some beautiful work in various places, single triplet qubits, for instance, from the Jacobi group, exchange-only qubits from Copenhagen, from HRL, ETH, other places. So we'll see. The last word hasn't been said. I think it's still an open question. So let me close with a bit of perspective on what a future large-scale quantum computer could look like based on spin qubits. And this image comes from a paper that I wrote with colleagues in the field, where we try to really paint a picture of what this could look like. We envision local registers of qubits, probably in 2 dimensions, at least a ladder, but probably 2 dimensions. We don't know how many we'll want in such a local register, but we do think that eventually, to keep scaling up, it will become advantageous to start building replicas of these local registers on the same chip. Instead of making the local register bigger and bigger, we'll just have a fixed size and then have a unit cell and replicate this. And that means that we need, of course, to connect these unit cells with each other through quantum links, coherent links on the same chip. And furthermore, what I envision is that in order to overcome one of the least profound but most practically important bottlenecks, to overcome the wiring bottleneck, we may have some local electronics in the empty spaces between these registers to distribute signals across the chip. The wiring bottleneck is the following. In the qubit experiments today, there is at least 1 wire going to every qubit. And that's fine for now. But if you want to integrate 1 million qubits on your chip, you would need to bring 1 million wires from the outside to the chip, and there is no technical solution for that. So therefore, having a limited number of wires and then having some multiplexers or etc. to distribute signals seems like a way forward. Of course, these electronics will dissipate energy, and then you need to check whether your qubits can tolerate the higher temperatures. So on the scaling up, there's been some work. I already mentioned the 8-dot array that we can tune up, easily now. There is similar work in silicon. This is gallium arsenide. This is from silicon. In silicon, a 9-dot array from the PETA group. Then there's also been first work on 2-dimensional arrays, mostly in gallium arsenide. This is a picture from us. And then this 3x3 array is from Tristan Meunier in Grenoble, where they could control, the position of the electrons in this 3x3 array. And so the qubit experiments on these larger arrays are happening. Most of the published work is, there was one other slide that I wanted to have, which shows, 3-qubit entanglement in a linear array from Terruccia, which shows universal 4-qubit control from Menno Veldhorst in a 2x2 array based on germanium. And then I wanted to show this unpublished work from our own group, where we have a linear array of 6 quantum dots. We have 2 sensing dots. And then you see here the contours of the cobalt, the micromagnet gradient, which separates the resonance frequencies of the 6 qubits, allows us to selectively drive. These are the chevron patterns driving the 6 qubits. We can control the coupling between the neighboring qubits by playing with the tunnel barrier voltage here. And if we then apply pulses, we can see beautiful exchange oscillations between all of the neighbors. So this is actually, I would say, state of the art. You know, a 6 qubit device is really fully under control. I see a question. Yeah, so the integrated electronics, I'll come back to that. Yeah, good question. Already we have played or programmed some small protocols, you know, creating multi-qubit entanglement and so forth, and we're in the process of continuing and quantifying that. So we're moving along here. As we move along, I think that eventually bringing in, and this is one of the real advantages also of semiconductor spin qubits, we can really bring in and leverage the multi-billion-dollar or euro infrastructure that's available in the semiconductor industry. And almost 6 years ago, we started a close collaboration with Intel, where the goal is to really apply the fully, you know, all of the industrial processing techniques and bring it to our field. So there's no shortcuts here. There's no e-beam lithography. It's fully optical. There's no liftoff. I mean, these are technical terms that only some of you will understand, but it's very different from how we make qubits in our group, for instance. And the result also is phenomenal control and homogeneity. You know, just look at the gate pattern here, looking at this at the cross section and compare it to a typical gate pattern that we fabricate in our clean room. And we have a good clean room. That's not the problem, but it's just a different approach, different technology. And so what we then, as a first test, did was to see whether one of those qubits that's fabricated with these methods still is well behaved, you know, because one thing is to have these industrial methods, but are they compatible with in the end getting a qubit that functions? And in fact, all of the metrics that we determined or that we extracted, I think are really in the ballpark of what people report. So in other words, industrial qubits, fully industrial, you know, made by advanced manufacturing, semiconductor manufacturing actually exists. I already see a question for the end of the lecture, but I can't take it here. So I mentioned it in passing, the 4-qubit work in germanium from Menno's group. And I think it's really impressive to see how fast this new material platform has moved along. At this point in the lecture, we can give some context to what was done there, right? So the method for controlling was to use the intrinsic spin-orbit coupling to control the spins. The 2-qubit gates were again driven by exchange, and the readout was done by Pauli blockade. The readout was not so high fidelity, but the control was actually quite good. And what's especially remarkable is how fast that system has moved from growing a material just a few years ago to you know, state-of-the-art measurements with universal control over 4 qubits. And yeah, like I said, there was one slide that I had meant to stick in there showing some of the recent multi-qubit work or published work. Now, in terms of building couplers, right? So these are the quantum links, basically, between the registers. There are several ideas published in the literature over the last 15 years or so. I think a very promising approach is to literally take an electron and displace it over the chip while preserving the spin state. And we have done some work in gallium arsenide testing this. Also, the Meunier group at CNRS has done this. And that's looking encouraging. And such experiments are now also beginning to be done in silicon. And we hope that we will get quantitative information on the fidelity of this of the spin preservation during the transfer from one place on the chip to another. The advantage of this approach is that it's just more gate metal, and it's fully compatible with the way that we make the quantum dots in the first place. There is a different approach which we've also been working on, and actually Pasquale will give a lecture about this in the afternoon. He's been, well, he did outstanding work in my group, but then later did really fantastic work also at ETH as a postdoc, using the superconducting resonators that are popular in the transmon community to couple also spin qubits, or and so I think one important step here was that the so-called strong spin photon coupling regime was reached, which means that the electron spin in the quantum dot interacted strongly enough with the microwave photon in the superconducting resonator that this interaction was stronger than the cavity decay rate and also stronger than the spin dephasing rate. And so that is called the strong spin photon coupling regime, and it's a starting point of future work, looking at coherence. And let's see, I see a question. All right, what are the challenges? Yeah, I'll come back to that. So let me show you here some unpublished work from our group. We're writing this up as we speak, where we actually were able to reach the strong spin photon coupling regime at both ends of the resonator. So there was a spin here, a spin there, in both cases in a double dot. We could reach the strong spin photon coupling regime, and we could also reach the regime where the two spins interacted with each other with an interaction strength larger than their dephasing rate. And the interaction is mediated by virtual occupation of the resonator. So it's the spin qubit frequencies are brought in resonance with each other, but they are away from the resonator resonance. That is to say, we're in the dispersive regime. And you see that here we maneuver one qubit splitting, we change the other qubit splitting, and then in this case, we change both qubit splittings together. And instead of seeing these lines cross, you actually see an avoided crossing. And from the analysis, the spin splitting here is larger than the line. It's actually what's interesting is that the upper branch of the avoided crossing is not very visible, and that's not because our measurement is poor. It's actually a signature of a dark state. It's expected from the way that that symmetry works and that the interaction works. So that's, I think, a next step. And Pasquale this afternoon will review in more detail the physics of these experiments and the progress that we've made as a community. There was already a question if we have this electronics integrated on chip, and that's another advantage of the silicon approach, right? You can have CMOS electronics side by side with the qubits. It's the same processing. Then the worry is that the chip will heat up. And to what extent will the qubit still work? So here is work from Menno's group, Menno Veldhorst at QTech, where they tested universal 2-qubit control beyond the Kelvin, getting quite decent fidelities for the first experiment. Also, the Dzurak group tried or tested single qubit control at well above a Kelvin. And ultimately, I think that there may be some compromise operating temperature. Of course, the higher the temperature, the more electronics you can have, the more sophisticated it can be, but the more you will sacrifice the dephasing time and the relaxation time, especially the relaxation time. We'll have to see what turns out to be the best operating temperature in this multifaceted trade-off. At the same time, already working towards this vision of bringing the electronics close to the qubits, we have here results. This is actually a collaboration between my group and then the groups of Eduardo Charbon when he was still at QTech. He's now at EPFL, or back fully at EPFL, and Fabio Sebastiano, Masoud Babai in Delft, and also colleagues at Intel. And so these engineering groups designed a chip that's specially designed to operate at cryogenic temperatures. and that's designed to offer, tailor microwave bursts to allow universal control of the spins. So it's quite impressive, actually, what this 4x4 millimeter chip can do. It can output 128 different frequencies. Each of them can be clipped in time. There can be amplitude profiles. There can be shape, phase profiles. It's really impressive. The quality of the signal, the quality of the signal intrinsically is good enough that essentially we didn't see any difference with the expensive and bulky room temperature equipment. The single qubit gate fidelities were 99.7 here, limited by the sample, and we had the switch going back and forth between room temperature and cryochip. We gave the same fidelities. And it's sufficiently flexible that we could even or already program some small algorithms on our qubits. So altogether, I think that this vision that we've put forward, the elements are actually being tested and worked out one by one, and I think that's encouraging. We have not run into any real showstopper. Of course, there's still at the same time a lot of work to do. One of the questions was, what are the challenges, basically? And I think that in the short term, a challenge that many groups face is reliable fabrication technology. I think eventually the fabrication technology of the industry will solve that problem for real, but at the moment that's limiting how fast our community moves. There are also, as we move forward, we every time run into new effects. It's, for 20 years we've been in this mode, like, let's rotate the spin, let's read it out, let's couple them together, let's do that with 3 spins, let's do it in silicon. And when you start, you think, how hard can it be? You apply an oscillating magnetic field, there is a spin there, it's going to rotate, it has to. But then, as Pasquale can tell you, when you do this in silicon, you figure out that actually in that experiment, initially there were 2 resonance frequencies for the single spin because of this other degree of freedom, the valley. And that's one example. And it's like that all the time. I've been amazed how often we have actually come across something unexpected, and there was some physics to learn that keeps it fun. It also means that things take time, and we haven't run out of running into things. So that continues to be going on. I should also say this multi-qubit experiment, we still have to quantify the fidelities. So we get multi-qubit control. We also got fidelities of 99.5% on the 2-qubit gate, but we haven't done that together. And that's, of course, a step that we need to make. And then, to deal with the crosstalk, there's still also some puzzles and questions surrounding crosstalk. And in the end, there are also just many practical obstacles to overcome, like with any qubit implementation. But, this being said, I am now more optimistic than I was before, than I was 10 years ago when we were doing gallium arsenide. And I also get optimistic from seeing that the elements for realizing this vision are coming together one after the other. And so, it's hard work, it's interesting work, and we continue to work on that with many people in our community that have contributed or are contributing. Then there is a question, how do you control the spin photon coupling? Yeah, I didn't explain that. It's the resonator that we're using in this experiment. It's a lambda/2 resonator, essentially. So it has a large electric field amplitude here and here. And the large electric field amplitude is made even larger. Well, okay, I'll skip those details. I'll just answer the question. The electric field couples to the spin through the gradient, magnetic field gradient from the cobalt micromagnets, like in the other experiments. And we can turn that coupling on or off as follows. If we force the electron into one of the two dots of this double dot system, then the confinement is so strong that the single microwave photon does not have sufficient amplitude to really appreciably move that electron around in the field gradient. And so there is effectively no coupling. If we put the electron, or if we tweak the potentials so that the electron hesitates between, do I want to be left or right? In that case, the single microwave photon, or the electric field from it, can easily displace the electron over a large distance, in principle as large as the distance between the two dots. And in this case, the coupling is turned on.
Excellent. Thank you, Lieven. I always find this very inspiring that all these things can be done on miniature scale, much smaller than the superconducting qubits that we build here. And I'm very curious to see how this evolves.
Yeah, me too. I actually did also put some study material here as a last slide, and I can share these slides if you want.
Yes.
I noticed that this line refers to something from a Delft course, so ignore that. But I think this is a review that has many of these concepts that I've explained, going through the DiVincenzo criteria, and it's yeah, a lot of people find it useful. And then there is a shorter article that I wrote in Physics Today that also summarizes the main elements and the outlook on scaling. And then there are some further.
Yeah, that was actually my last question. My next question, if you can just email us the slides, we'll distribute them after the school to all the applicants. And
yeah, I'm happy to do that.
Exactly. Yeah, that's fantastic. Cool. I see. That's not a question. Okay, and then the chat, there's just people thanking for the presentation. Okay. Then, yeah, thanks again. And we'll reconvene if there's no more questions in Gather for the Qiskit tutorial session by Ali Javadi. And that's at 2 o'clock after lunch. And after that, we have Pascal first, right? Yeah, Pascali Scalino, who's also in this room right now, at 16:15 in this Zoom channel. Yes, exactly. Thank you, Max. All right, then everyone enjoy your lunch and see you in 1.5 hours.
Bye-bye. Thank you.
Thank you, Lieven.